So hi, I'm Tim. Thanks for coming to the talk this morning. Basically going to talk about some of the stuff I've been doing lately with Storm and when I got the idea for this presentation, it was really just based on kind of wanting to share lessons learned and what I've done, and then kind of cover some of the things where I see Solr being used in more real-time stream processing applications. Let me take a quick kind of poll. Who knows what Storm is? Okay, and out of those, how many of you are like using those in production apps right now? Okay, okay, good. So most of this will be useful to you then. So who I am, just a little bit about me. Right now I'm sort of an independent consultant on search and big data projects. I have a background in a lot of Solr, the Hadoop stuff, some NoSQL. Solr is probably the nearest and dearest to my heart. And then recently, like the last year, been doing a fair amount of Storm work. I'm going to, in December, be joining LucidWorks on the engineering team. I'm also the co-author of Solr in Action with Trey. He's running around the conference here as well. If you want to look at the book, we have a printout copy. We're really close to going to print. Has anybody bought the MEEP or started reading that book? Okay, all right, it's a beast. Sorry guys, hope you're getting a lot out of it though. And then I kind of did a lot of the Storm we're going to talk about today for the Dotchess group, which is based out of Austin, Texas, and they do social media analytics for major brands. So how I sort of got started with Storm is we had this very cumbersome Hadoop-based, a lot of pig, Oozy, some Hive, some scooping over data from databases, and it was really intended to build this indexing pipeline. So we wanted to take in data from all the social networks, Facebook, Twitter, what have you, enrich that data, various different enrichment processes, sentiment analysis, language detection, basic stuff like that, as well as some of our internal type enrichments we needed, like for conversations and relationship. And that was basically bogging down. How many here are doing stuff with Hadoop and like feeding a Solr index right now? Okay, okay. Yeah. Well, definitely look into this as well, because so we had that and it did work, but it was very cumbersome, and I would have to tell the business customers, yeah, it'll be a couple more hours before that tweet is visible in Solr, and that never really went over too well. So we took basically this cumbersome batch-oriented process, ported it to Storm, and now it's less than a minute between when we collect a tweet to when it's actually visible in Solr, which is that makes a lot of things a lot easier. We still use Hadoop for deep analytics and that kind of thing, so it's a mixture, sort of a hybrid architecture there. So today, and it looks like most people here are pretty new to Storm. There are some other talks about Storm at the conference that I think are really going to be a little bit more advanced. I'm going to focus more on just kind of, what are the things you have to think about? What do you need to know to get going with Storm? And then we'll look at some kind of common integration points that I've worked with Solr. Basically, the obvious one being real-time indexing, Percolate feature, which is stealing a term used by the Elasticsearch product, which is basically you have a number of predefined queries and you want to match those to documents as they come through. And then one that's probably not as obvious but pretty simple is just using real-time gets and kind of Solr as a NoSQL data store to kind of fuel some of your other real-time applications, and we've been pretty successful with that, so I'll talk about that briefly. So let's get started. This doesn't really have much to do with Solr, but it kind of gives you a way to start thinking in Storm and stream processing. So the example I chose is essentially when anybody searches on this URL shortener 1.usa.gov, and that shortener will do any links in the U.S. government. Whenever somebody clicks on that, that will generate this event on this stream. Sorry. And for example, if I clicked on the one USA Gov, it would take me to the smartgrid.gov. But this stream of events basically shows how people are using US government sites. So that's pretty much a classic example of a stream that you'd want to process. And for today, we'll just say we want to come up with, what are trending sites? What are some trending government sites? And we'll use Storm to compute that. So I chose this because, most of the time, and if you've even looked at Storm or you can remember Hadoop, it's always word count, right? How do you count? You count words, which is interesting, but it doesn't really kind of, for me, it didn't show me all the things I was going to have to think about as a developer using Storm, because as soon as you got through word count, in no particular order, how do you unit test it? I need a database connection to get access to various metadata. How do I get access to that and manage it? Any kind of web services, how do I get those dependencies? Runtime behavior components, is your Solr, say we're doing a real-time get, is it slow? And, so kind of keeping track of various metrics. And then, some of the other ones are pretty much what you get into Storm. There's a lot of boilerplate that you have to implement very correctly, or you get a lot of weird behavior. And honestly, as most developers, we hate boilerplate, right? We want to focus on the business problem at hand and kind of let the framework handle the rest. So these are things that actually I wanted to ensure I had as I started working with Storm. And so kind of going back to what we did with the Dotchless group, we started out with one Storm stream processing application about 6 months ago, and in the last 6 months probably developed another 10. So all the needs to have reusable code and those kind of things have come up. So to get in, before we talk about the actual implementation, let's cover what Storm is. This is pretty much right off their website. Effectively, you take a problem and you take a message in a stream and you essentially send it through and do various things with it. And Storm ensures that that's scalable, fault tolerant. You can set it up so that Storm guarantees processing the message, or at least will tell you if that message can't be processed. And so when you first start out, you're going to encounter sort of some interesting primitives that you just kind of have to understand. And they're not too difficult. Tuple, I'm not a fan of that because it kind of sounds more complex than it is. It's essentially just a list of values, an ordered list of values, So you kind of, as a developer, have to know what's expected in slot 1 and 2 and 3. So that's a pretty low-level concept in Storm. A stream is going to be just basically an unbounded sequence of tuples. And what that means, really take that to heart, because when you have a Storm application or any kind of stream processing application, it's always running. And you kind of have to plan for that it's always going to be running, which is very different than batch mode. And we'll talk a little bit about how Storm helps you deal with an app that's always running, because it's definitely a concern. There are two basic components that you as a developer will implement, and we'll see some examples of these. The first is the spout, and that's essentially the message producer into your stream. And on our example of the government shortener, we'll develop a spout to do that. And then bolts are the other type of main component that you as a developer need to worry about, which do some operation. And bolts can kind of do a number of different things. But they're effectively working on the message as it processes through. And then this essentially directed graph of spouts and tuples in Storm is called a topology. Again, I think the originator of Storm liked to sound very, I guess, sophisticated. I'm a math person, so topology to me means something different. But topology here is basically you build up some directed graph of spouts, and that should actually say bolts, not tuples. Sorry. Okay, so for our example, it's pretty obvious. We're going to receive some events from this stream. And again, you can imagine that could be Twitter. That could be anything that in your environment would produce events, right? And then what we're interested in is the, like trending sites. So we're going to have to count the frequency of pages, right, in some time. When you're talking about the top N, it's some time window, you know, in the last hour, depending on like if Twitter, where Storm is sort of really fleshed out. Obviously, they're working more in minutes and that kind of thing. For us, it could be, you know, like a 10-minute window. What are the popular government links in 10 minutes window? And then there's also the need to sort of, well, we know what the top N are in the last 10 minutes. We need some metadata about those. So we want to extract from these links, you know, the title, maybe some of the body text, representative image, that sort of thing. And then you may want to, and we actually won't touch on the bottom as much because that's pretty much like database storage. I don't think you guys want to be bored with that. But you need to persist them in some store for visualization. And in fact, it could be actually Solr for that. This slide is not that important. It's just basically I took a snapshot coming off the wire from this topology of some stories that were trending in the U.S. government on September 12th when I was kind of working out some of these slides. A lot of NASA traffic, and I don't know why that is. Just from what I can tell, a lot of NASA traffic. But if there's some big event like some scandal at the White House, that'll be trending, that kind of thing too. This is interesting in the circle there. This is some rocket launch, again, NASA, and I thought this was pretty cool because it was trending. People were digging that poor frog who got launched up in the air. I don't know what happened to the frog, but that's kind of an example of, you know, again, tapping into the sort of collective intelligence, people trending interesting things. So let's dig in now to the solution for this, for our first storm topology, and kind of start over here on the left-hand side. And I apologize, pretty detailed slide. You'll be able to get slides at the end, so we'll just focus kind of on the high points. So I mentioned we need a spout to actually produce tuples into our stream, and in this case, the spout simply just subscribes to that stream provided by the one USA Gov shortener and injects those messages into this topology. Okay, and then you can see what I'm doing here is I fork off, and on the bottom, we'll focus on that for a second, I run it through various bolts, and these bolts do different things. Their main job is to actually come up with a rankings, you know, which links are popular in the last 10 minutes or whatever. And the nice thing actually is Storm will provide these bolts right out of the box. The Storm comes with a starter project that you can download. It's written in Java and probably some Clojure as well. But you can use these right out of the box. Like I basically pulled these into my topology and used them as is, which is nice. So definitely, as you get started with Storm, check out the Storm starter project. It's also on GitHub. And then you want to, again, persist the rankings. And then up here is that metadata enrichment. And that's where we take a URL, send it to some service. In this case, I'm using a simple web service called Embedly. We'll talk a little bit about that in a second. And the idea there is we want to go ahead, follow that link, extract out some metadata from the page, and then probably a good idea is to index it so people can search. And you can obviously imagine a blend of the metrics, you know, top queries, and then, you know, doing some full text search. Let me search for frog or NASA or what have you. So that's kind of the really basic layout of this here topology. So let's dig into some of the kind of subtle aspects of this that you as a developer with Storm need to kind of grasp. So the first one is stream grouping, and this is pretty key to understanding how Storm works. And for those of you that are sort of familiar with the MapReduce model, this is kind of how stream grouping, very similar to sort of how you decide which data goes to reducers. You know, sometimes if you're doing a join, it's based off the join fields. But Storm essentially allows you to decide, as my bolt emits, or it could even be my spout, emits these tuples into the stream, I need to decide, you know, when they're going into the next step, do they need to be grouped in any sort of fashion? And shuffle is just a random distribution. So if you have 100 bolts in the next step, well then Storm for you will just go ahead and distribute randomly the tuples across those 100 bolts. Another common one, and we can see this back here, is field grouping. So you're going to go ahead and group the tuples by one or more fields in common. Can anyone think, in our little example here, what would be useful to use that field grouping for this layout? Kind of giving the answer on there, but yeah. So in both of these, we actually want to group by the URL. And so what we want to do is, since we're counting occurrences of URL, that's sort of the word count area, we actually want to group the stream by the same URL. In this case, I'm using the bit.ly hash, which is a unique value for each URL. And so that basically ensures that as I see these events, I'm sorry I keep touching that, as I see these events, clicks on the same URL go to the same bolt. And that allows that bolt to then keep track of frequency per URL. And so that's all built into Storm. You just decide, okay, when you build your topology, you say, I want to send all of the tuples to the same bolt grouped by the bit.ly URL field. Global is another one. That's where you want to basically reduce all of the message down to one bolt. And the use there would be, you know, maybe you're saving it to a database and you wanted somehow ordered or whatever. Various reasons to use global. The one I haven't used, which is almost kind of like you can think of it as a cross product, I guess, is you would replicate the tuples to all instances of a bolt. I haven't found a use case in my doings yet for that, but it's there if you need it. Okay, so some other things from that diagram that I think are useful that confused me when I first started out is that, first off, you can have many spouts in a topology serving into any bolt, okay? You know, in my job, we, again, listened to many different social networks and had, you know, hundreds of data sources that we pulled from. And so some of those had different spouts because of how to work with those data sources, but they all fed into the same bolt. So you can definitely, you know, you're not limited to one particular type of spout here that you have to make work for you can spread it out. We've talked about grouping. Another one that is, and we saw an example of this, is that you can actually split streams off, and so send to different parts of your topology. And a good example there is actually link extraction. It takes a long time, especially when you're talking about like an indexing pipeline or whatever, to go and say extract and resolve a shortened URL. You know, say you get a tweet in and you need to know what's the actual page that resolves to. Well, that's actually takes a lot of network hops, because a lot of these URL shorteners are like 6 different redirects before you get to the actual page, and then maybe you even want to process that page. So you can actually split off and you know, send that down, and it takes a little bit longer, and then possibly join it back with another stream if you had to. So that was something that, you know, it wasn't immediately obvious to me when I looked at this, but it's come in very useful. Excuse me. Another thing is that actually bolts can inject new tuples in the string. So as you get a message, that tuple may require you to create, you know, additional tuples based off of it, and Storm actually allows you to keep track of those, and it's almost like a what they call a I believe it's a base or root tuple, and Storm will keep track of all the tuples that came off of that root tuple as you're processing the stream. And then sort of these we'll talk a little bit more about parallelism level, but so you can actually have Storm optionally keep track of messages as they're entered into the stream. So and that's useful for where you know, you need to know this message was fully processed by the topology before I do something else with it. And again, that's something provided by the framework that you have to know how to use that feature, and we'll talk about that in a second. So since we're not doing just basic word count, I'm going to talk about some of the tools we used. This is not me trying to impart any sort of framework on you. It's just that these came in handy for us for achieving some of the things basically that that we were looking for in our topology development. So Spring, a lot of the source code examples I'm going to show you in this will actually be in Groovy instead of straight Java. And then we use like Mockito for testing, and then some like Codahill metrics. Netty is what I actually use. That's a pretty awesome networking library if you've not checked it out. Okay, so let's dig into the details of this spout. Basically, it's pretty easy, right? You just read information off that one USA Gov stream and then produce tuples into your thing and forget about it. Except in this mess down here is actually intended to kind of just be a mess, in that there's a lot of other sort of policy things in Storm as a developer you have to kind of take care of in your spout, such as, you know, easing off the throttle. If your topology is not keeping up with the data coming in, you have to handle that, or you're just going to end up essentially the topology gets so behind that messages will be failed. They'll time out, and Storm says, okay, it's timed out. We're going to have to, you know, reprocess this message. So you just end up turning into this kind of, you know, soon-to-be dead topology if it can't keep up, if your spout is producing tuples too fast. So there's a lot of things you have to deal with within a spout. And so what we came up with is, well, there's a lot of complexity in implementing spouts and bolts correctly to sort of adhere to the Storm contract, and then there's the business logic. Okay, and I chose Spring. It's popular. If you don't like Spring, there's other ones, Juice, that kind of thing. But this came in really handy, is to actually have a Spring container sort of bootstrapped into our topology per JVM. And then it does all the things that Spring does, you know, manage JDBC connections, all this kind of thing for you, and it gives dependency injection into our spouts and bolts. The problem is that Storm, the framework, initializes these. You don't have control on who news these objects out, right? These are actually by Storm, but which is fine. So we let Storm go ahead and create those when it deploys your topology, and then we actually do some you know, basic lookup into the Spring container to actually get the business logic. And so this is the design we went with that essentially allows you to get all the nice things you get from having just POJOs that don't know too much about about Storm, and they get all their dependencies injected, which makes it a lot easier to test and those kind of things. So here's an example of one for this example we're doing, the One USA streaming provider. I've kind of pared down the code. You can see right here, message stream, that actually is essentially an abstraction over the Netty, which I'm using to go ahead and process and get the messages from that source. And then whenever we need a new tuple, we basically, the framework, that Spring spout, goes ahead and calls this next method, which the job of this is just to pull it off parse it, pull it off the queue, internal queue used, parse it into something intelligible, and then produce a tuple. And the name values there is just, again, I said a tuple is sort of this ordered list of values. This is more of a map concept that knows how to create a tuple for Storm, but it actually allows you as the developer to kind of work more at a name value pair type of level. And so this here is probably 90% business logic. Obviously, the business logic of a stream data provider is not all that interesting. But the idea here is this is a Spring managed POJO with dependency injection and access to all the Spring stuff. For example, one of the things Spring does nicely, and a lot of other frameworks have, is like the ability to convert from JSON to Java. And I'll show you an example of the JSON, but trust me, basically coming off that One USA Gov stream is this really kind of compact, nasty JSON string that, if you can see these, for example, it uses the user agent. It's just in the JSON, it uses the A field name. Well, that's not very useful, and you don't want A all over your code, right, if you needed to get access to the user agent. So I'm just basically transforming using built-in Spring stuff. When I get these JSON messages in, I transform them to serializable Java objects, which makes it easier on the developer. And that's nothing groundbreaking, obviously. The point is, just because you're in Storm, don't think you have to kind of bail out on proven methods. Just map JSON or whatever format it is to an object, and then kind of that makes your business logic a lot easier to work with, that kind of thing. And so the actual provider bean, the POJO, is just set up in Spring in our case, as a bean in the in the Spring configuration. And this is actually how we set it up when we're building the topology to submit to Storm, which I'll talk about in a second. One of the nice things is this is really easy to unit test now, because we've taken away all the need to kind of have anything related to Storm in our business logic. Okay, and so there's the JSON. There's an example of it. You can see it's just pretty much, it's like machine code more than user friendly. And then we just go ahead and send it into, we create our data provider. In some cases, like here I'm using Mockito to go ahead and mock a message stream because it's not part of this unit test. Don't need to beat that into you guys. I'm sure you're all familiar with test-driven development and making kind of unit tests. Just test the key logic there versus trying to build an integration test. So the point is, now I have all my data, my business logic of my Storm topology. It's all just basic Java objects that are easily testable and that sort of thing. Okay, so let's talk about, and this is sort of the bottom of that diagram, which was how to compute, the top N. And I don't want to spend a lot of time on this because it is sort of provided by the Storm Starter project. This gentleman here, Michael Knoll, he kind of revamped all that code and wrote a good blog on it. So if you have a top N type problem, accounting problem, in a certain time window, definitely go check this out. I won't spend a lot of more time on that because, again, it's just for this example to kind of support. Okay, so one of the bolts I had to build is this the enrich link. So we see a link, we're going to go out and get the title and representative image and that kind of thing. And so in this case, it calls out to a web service, happens to be Embedly. And does some local caching because we don't want to go out and hit Embedly, because remember, we're sending the same URL to the same bolt. So he's going to see the same URL sometimes. It only wants to go to Embedly once. So you use some internal caching. Again, relies on the field grouping, and at the end of the day, it's going to go ahead and index in Solr. So one of the things, and this is kind of getting into more of the thinking in Storm, is going out to that web service, and Embedly can take some time. You can process more links by just increasing the parallelism of that bolt, and that's what Storm provides. So Storm will say, you'll tell it, we need 50 bolts across my cluster to do link enrichment. So then Storm will sort of provision that around your cluster, and if any of those fail, it'll reprovision that. So it handles all that kind of distribution and that kind of thing. Of course, if you're calling out to something like embed, don't overdo it because you'll blow past rate limits and get blocked and that kind of thing. But the main point is that really Storm, the framework, allows you to kind of distribute out heavy load work, that kind of thing. This is just an example again of using Spring to implement a service. It could be a Solr service. In this case, it's just embedly, and it's a good sort of segue into one of the other things that we found when we were building Storm is that Storm gives you very high-level metrics, like kind of how quickly it's processing the message. Very coarse-grained. You're moving 1,000 tuples through this bolt every second, right? It'll give you that. But what if Storm shows you you're moving 10 tuples through this bolt and you have no idea why? So we found that we actually needed to kind of supplement the Storm high-level metrics with some finer grain stuff, and we ended up using CodaHill metrics, which I think was originally developed by Yammer. Is everybody familiar with that? If not, it's a really awesome Java library for implementing, histograms and rate counters and that kind of things. So definitely worth looking at. We integrated it in with some just real basic kind of groovy closures and whatnot to make it really easy for the developers to, again, just focus on, well, I need a timer to keep track of, how long is embedly taking and that kind of thing. So definitely look at that as you kind of step into the Storm world. And they report metrics out to JMX and all the different kind of tools, Ganglia and Graphite, and they also have a plugin framework where you can build your own sort of endpoint for doing reporting. There's an example that spits out, don't worry about it, it's small font, but like how many times I'm calling Solr and that kind of thing. Okay, so that's basically kind of some of the things you have to think about when you're developing topology. Let's look at some of how Storm scales. Okay, so these are the basic actors. A Nimbus is sort of this master node that handles the deployment of topologies, uses a Zookeeper behind the scenes. Every node in the cluster has a supervisor, which sort of works with the worker processes on that node. Workers are full JVM processes, so you just fire up as many of those as your hardware can support. Allocate memory accordingly, all that sort of thing. And then there's these executor pools, which are basically thread pools in each worker. And then executors execute these tasks for a spout or a bolt. Okay, so starting up here on the top left, when you as a Storm developer, you need to produce a jar file, a lot like the Hadoop jar. It has all the dependencies resolved and everything built in there. And you submit that to Nimbus, and there's basically a command line tool that you provide the jar, and then Nimbus goes ahead and deploys that out to M number of nodes using the supervisor. Okay, and then obviously the supervisor knows how many workers, and again that's pretty much based on your hardware. And so think about it. If I say my enriched link bolt, I need 100 of those, and I have maybe a 10-node cluster, it'll probably be provisioned out on 10 workers on 10 nodes, that kind of thing. And Storm handles all that for you. If this worker, say worker 1 here, crashes, the supervisor will know that, and again, Storm keeps track of all the work it's kind of tasked out to each worker, and so it can kind of reroute that if this worker crashes, because it knows which tuples haven't finished processing, and so it'll send them through another worker, and that's kind of how it achieves the fault tolerance. A couple subtle things. This Nimbus seems like a single point of failure, and it is, and I believe there's some work to actually work on that. And as a sidebar, Hortonworks is working on kind of putting Storm in Yarn, so you can kind of run Storm and Hadoop in your same cluster if you're on Yarn. But anyway, if this fails, the actual work keeps happening, right? The workers don't like stop working if Nimbus is gone. So that's one nice thing about Storm, is that like this node can fail. You won't be able to provision any more new topologies, obviously, until that comes back up. But existing work, as long as the workers are healthy, we'll keep going through. Okay, so this shows some code, just for those of us like to read code. This is sort of me setting up our example topology. There's the spout, okay? And the parallelism hint, I'm saying 1. It's a pretty low volume spout, so I don't need more than one kind of listener to pull those off. So I only have 1. Again, if the worker hosting this spout dies, Storm will just fire this spout up on a different worker, right? And it'll keep going. And Storm knows, all right, well, I only need 1 of those. So if it goes away. And then here's the next thing. This is my enriched link bolt, which we talked about. It's that spring bolt, which again, the spring bolt does most of the policy stuff and keeps the developer from having to do a lot of Storm specific things. The fields grouping, as you can see, we're grouping on this global bitly hash. That's just a static I defined. And then again, the parallelism here is 3. It could be higher for an enriched link thing, but it was just for an example. So I just want to show you can have more of these. And so that means I'll probably be hitting the embedly API with 3 bolts concurrently. And one thing that, like I mentioned in the grouping was the global grouping. What if you have a web service that has a really strict rate limit? You could use the global grouping to kind of send everything to 1 bolt, hit that web service within the rate limit and that kind of thing. So that's where those groupings come and become useful. Okay, so as I expected, I'm running a little slow. But let's talk about Solr integration points, since we are at the Solr conference. So one of the first things we realized is that using real-time gets, for our work, we had the need to actually go into Solr for previous index docs and pull out metadata. And the real-time gets work fantastically. So we're actually almost starting to use Solr a bit like people have used Cassandra in the past for these primary key lookups. We don't do incredible volume, just given the service, but that has served us really well. Of course, you can do near real-time indexing with Solr from Storm, which is kind of a sweet spot. And then also Percolate, which I want to have a few minutes to talk about. So here's an example of doing a real-time get, again using a Spring service. Has nothing to do with Storm here. But bottom line is you just send the doc ID to this get handler that's built into Solr, and it'll return back the document. The nice thing there is that document does not have to be committed before it's useful, which is nice because, again, I don't want to have to commit all that often to support some high volume indexing. So anyway, you can get documents that haven't been committed. That's kind of the bottom line of real-time gets. Near real-time indexing. So one of the nice things now that's available in Solr is the Cloud Solr server, which is a client thing in SolarJ, can route documents to the correct shard leader. So it used to, you would send a document into Solr Cloud. Any node would take that and then decide which shard leader the document should be routed to. So there was a chance that there would be an extra hop. Now that can be done actually on the client because Cloud Solr server is sort of the cluster aware. It talks to Zookeeper to get the cluster state and that sort of thing. So if that's interesting, how many people are actually using Solr Cloud right now? Okay, some. So that's not useful to you unless you are using Solr Cloud. This I wanted to mention is for the hard commits. So as we're indexing from Storm, we're just constantly sending in docs through the stream processing. And we want to, and this is probably, again, more of a Solr Cloud thing, but we don't want the transaction logs, the update logs that Solr Cloud uses to grow too large. And so the new trick is to go ahead and configure auto commits for more frequent than you're probably used to in the batch world, which essentially kind of does the internal housekeeping of closing out the transaction log and flushing segments and that kind of thing. But it doesn't mean you have to necessarily pay the price on the searcher side. So you can say, you know what, I'm going to commit every 15,000 docs through my Solr indexing topology, but I want to control when I actually open that searcher. And then combined with soft commits is how you can also end up getting sort of, nearer time searches. I don't use soft commits as much just because our queries, again, a minute, if you see a tweet between a minute, that's usually pretty fine for our use case. Most of our stuff is more analytics on top of social data versus kind of real time like you'd see like at Twitter and the keynote that we saw today. And then again, you just go ahead and use Storm's parallelism to distribute out n number of indexing bolts, right? And again, that's kind of all built in there. I want to refer you to this, I think it's a blog or whatever, out on Search Hub, if you're interested in transaction logs and soft commits and that sort of thing. Excuse me. Okay, so let's finish up real quick talking about the Percolate feature, which is another thing we built into our streaming topology. And the idea here is sort of what I've heard it's called inverted search. Percolate is what the Elasticsearch guys on it. Google has a Percolator. It's not the same thing. So I don't know where the Elasticsearch guys came up with that idea. But the idea here is that you have documents flowing through this topology, and you want to decide if that document matches some pre-configured number of queries. And there are actually some additional talks at the conference on this, so I think it's a pretty common use case. For us, it was, is this tweet coming through our topology related to some campaign for some brand? These brands run campaigns, and they want to know, are people sort of responding to the campaign and that kind of thing. So what makes a campaign, in our case, is a pretty complex Solr query. And so now we can effectively match documents as they come through to campaigns was our use case. And so we're going to go ahead and use Storm for that. Two possible approaches that I'm aware of. I'm sure there are more out there. So there's a Lucene-only solution using memory index, and you could do this in Storm. And so Charlie and Alan are going to talk about this later today. So I definitely, if you're interested in that. They're solving a lot harder problem than I had. They have, like millions of queries they have to evaluate against each doc. I'm more in the thousands level. So the approach that we took was, well, we wanted full Solr. We didn't want to kind of bail back and have to revamp a lot of stuff that it was just pure Lucene. Because this memory index thing actually, it's an enhancement above like RAM directory, and its use is really for only having a single doc. And so it's pretty awesome. So especially if you have, really, really a lot of these pre-configured queries. We went that so we can have full Solr. We're using the RAM directory because I really have no need to flush these documents to disk. And then for processing number of documents per second, I use Storm's parallelism. So what it basically means is if I need to process 1,000 documents per second, and it takes me a whole second to evaluate, say, 50,000 queries per doc, well then I just go ahead and set the parallelism on that the bolt that does this to 1,000. Obviously I have to have a big cluster, but you get the idea. And again, I think this is a very kind of easy solution for up to a few thousand queries. This is the kind of design we came up with. So you can imagine, again, some spout, and then we're using here the random stream grouping, which just randomly distributes the the messages to be matched, the documents to be matched to different instances of percolators. There could be hundreds here. And in each percolator bolt, it actually instantiates a Solr server. So if you remember, you have to submit a jar to Storm. And so what we ended up doing was just taking our entire Solr instance directory that we cooked up for this, zipped it up and put that in the jar. And then when the bolt initializes, it goes ahead and pulls that out of the jar and extracts it locally so that you can then create this embedded Solr server on the fly. And so that worked out pretty well because it gave us, again, all the power of Solr, schema.xml, all those kind of things. And then the other insight there as well, we're keeping our queries stored in a database because the people that create the queries are actually business users, business analysts, and they'll change those at times. And so what we did was these guys can go ahead and when they're initializing get the list. But as this is running, if one of the filters change, we didn't want the kind of this constant herd effect of all these, polling the database or whatever. So we ended up actually just using this pub sub kind of framework for 0MQ, which the reason we chose that is Storm is built on 0MQ, so it was kind of already available, and it's a fantastic also networking library. Use that. So essentially, if you change a query, that gets pushed out into these, and they automatically get updated. And so that worked out really well and was fast to implement. And again, we rely on Storm to actually do the distribution and scaling for us. And again, we're kind of achieving, just given our volume, like 200 per second against maybe 1,000 queries. So it's not a lot of work. And you can go to later talk if you have a lot more work there to do. The last thing I want to mention, and I didn't really get to it, is, but it's something you should be aware of about Storm, is the concept of a tick tuple. You can configure Storm to essentially send in a special tuple to your bolt every minute or every 30 seconds. This is built into the framework, and you can see here that's basically what you have to do. And if you do that, you can do special work. You can do a commit to Solr. In the case of the Percolator, I do some housekeeping on the embedded Solr server to delete docs that have accumulated, that kind of thing. So this is a really handy little tool if you need to kind of do, it's kind of like a cron job, support for a cron job in your bolts and spouts. And so if you look at the slides, these are kind of some of the resources I use to kind of put this presentation together. And then I do have the code, all you saw here, checked in. So it should be available on GitHub, the lab dude, LSR Dublin, if you want to look at that. That's all the kind of the spring bolt and the spring spout and that kind of thing. Just give you an example if you're getting started with Storm. And then also, as far as the book, Manning is kind of providing some coupons for conference-related books, Taming Text, Solr in Action, that kind of thing. So I'm a little over on time, but are there any kind of quick questions? If not, we can take it off in the hall. Okay, I better get off, guys. You can track me down if you have more questions. But thank you.